All right, so recall that last time we started talking about LP spaces. Now, this is a topic that you probably have seen something about in functional analysis. We may not do everything here in full detail, but we will talk some amount about LP spaces. Basically, you know what LP spaces are. You have a measure space. A function is an LP if when you take its absolute value and take the pth power of that, then the result is integrable. In other words, the function is an LP if and only if the pth power of its absolute value is integrable with respect to whatever measure you're dealing with. LP spaces have some nice properties. They end up being vector spaces. They also end up being Banach spaces, actually. And we want to explore some of their properties. Now, of course, in the context of probability, you will, instead of talking of measurable functions, you'll be talking about random variables. And a random variable will be an LP if when you take its absolute value and then take the pth power of that, and you take expectation, you get something finite. All right, so let's get started here. I'm going to go ahead and turn off the video and share the iPad screen with you. All right, I think the screen should be visible now. So let's just quickly go over what we did last time. We're talking about LP spaces. So let omega f mu be a sigma finite measure space. Suppose f takes omega to r bar. Remember what r bar is. R bar is just, okay, no, just let me. R bar is just the extended real line. So this is minus infinity, infinity with both endpoints included. So suppose I have f taking omega to r bar, which is f b of r bar measurable. Then for each p in 1 infinity, so note that here 1 is included, infinity is excluded. I'm going to define this symbol. Now this symbol looks a lot like a norm. And the reason is that eventually we will show that this is in fact a norm, but right now we don't know that. Anyway, we define this symbol, this norm symbol f sub p to be, take the absolute value of f, take its pth power, integrate it with respect to mu, and then take the pth root. Okay, and similarly, if so, this is for p in 1 infinity, and if p is infinity, define the symbol f infinity to be the infimum of all non-negative numbers k, such that the function f is less than k mu almost everywhere. Now, if there is no such number k, of course, you'll get the empty set here. And of course, if you get the empty set, the infimum of the empty set is infinity. All right, then we said that note that the quantities, this symbol, this norm fp symbol, for p in 1 infinity, these are well defined, though they may be infinity. Because here, before integrating, we're taking absolute value, then we're taking the pth power, and then we're integrating. So the worst thing that can happen here is you'll get infinity, that's it. Similarly here, the worst thing that can happen is that this set is empty, in which case its infimum is infinity. All right, so now we're going to define what LP spaces are. So for any p in 1 infinity closed interval, let LP of omega f mu, which we will sometimes just abbreviate to LP of mu, let this be the set of all f taking omega to r bar, such that f is measurable, and you know what sigma algebra is involved, and this norm symbol f sub p is less than infinity. Okay, so LP of omega f mu is just the set of all f taking omega to r bar, such that f is measurable, and this norm symbol fp is less than infinity. Now, what is this norm symbol fp? This is just the pth root of this integral. So for the pth root of this integral to be finite, that will happen if and only if this integral is finite. Okay, so note that for p in 1 infinity, here infinity is excluded, note the open interval there. A measurable f taking omega to r bar is an LP if and only if absolute value of f to the p d mu when integrated gives me something finite. Okay, then what did we do? We said that for any 1 less than or equal to p less than or equal to infinity, we said LP of omega f mu is a vector space. We went over the case when p is in 1 infinity last time. And the case p equals infinity was left to you as a do-it-yourself assignment. All right. Now the next thing that's happening is the following. We already know, because we have heard rumors perhaps, or taken functional analysis, or perhaps flipped through some book. And based on that, we know that this is actually going to become a norm. Now, of course, there are going to be a couple of minor things we'd have to do before we make it a norm. But in anticipation of that, let's remind ourselves what a norm is. So suppose I have V, which is a real vector space. Okay. Now, norm is typically denoted by this symbol. You have seen this. So what is a norm? A norm is a function, this symbol taking V to R with the following three properties. First is that the norm of x is greater than or equal to 0 for all x in V. And further, norm x is 0 if and only if x is 0. Now remember, here when I say V is a vector space, it means that V is a collection of objects which I'm calling vectors. These are abstract objects. They may be the vectors you learnt of in 12th standard. They may be n-dimensional vectors you learnt of in college. They may be matrices. They may be functions. But basically, the vector space is a collection of objects which has two operations. Vector addition, you can add two vectors, get a new vector, and you can multiply a vector by a scalar and get a new vector. I was a little careless. When you talk about a vector space, you should also specify what the corresponding field of scalars is. So vector space doesn't come on its own. The vector space comes with a field of scalars. So, okay. So basically, when I say a real vector space V, I have a collection of objects called vectors. Such that for any real scalar, I can take scalar times vector and I get a new vector, and I can add two vectors and I get a new vector, and a whole bunch of criteria are satisfied. And anyway, this norm symbol is basically an idea, a notion of length. Okay, so what the first property is norm of x greater than or equal to 0 for all x in V, and norm x is 0 if and only if x is the 0 vector. By the way, here when I write x equals 0, you should not be thinking that this is the scalar 0. It is not the scalar 0. This 0 here refers to the 0 vector in V. Okay. Secondly, norm of alpha x should be absolute value of alpha norm x. This should be true for any x in V and any alpha in R. Finally, norm of x plus y should be less than or equal to norm x plus norm y for all xy in V. The third one, of course, is called the triangle inequality. Anyway, where are we going with all this? Well, where we're going with all this is that we have a suspicion that on LP space, the symbol which we have denoted using a norm symbol is actually a norm. But that is not actually quite true. We will see shortly that 3 can be proved, 2 can be proved. The first part of 1 is okay. It is in the second part of 1 that there is a subtlety where we have to do a little bit of clever footwork. So let's get to that. Okay, so let f be in LP of omega f mu, all right, where p is in 1 infinity. All right. Now, of course, omega f mu is your measure space. So note that this symbol is greater than or equal to 0 always. Right? Also, if f is 0, namely if f is the function which is always 0, then norm fp is 0. I will leave it to you to check this. Okay, if f is the 0 function, then its norm symbol or whatever is going to be 0. Now suppose norm fp is 0. Does it follow that f is everywhere 0? Answer is no. It may not be the case that f is everywhere 0. What you will be sure of is that f is 0 almost everywhere. So there may be a set of measure 0 where f may be non-zero, but other than that, it's going to be 0 everywhere. So here, we can only conclude that f equals 0, mu almost everywhere. Okay, so now let's come back to this requirement number 1. For any x in V, norm x must be greater than or equal to 0. We have that. Okay. For any f in LP, norm fp greater than or equal to 0. I'll leave it to you to check this. Okay. I'll leave that as a do-it-yourself. What does the second part say? Second part says norm x equals 0 if and only if x is the 0 vector. So suppose instead of x I have f. Suppose f is the 0 function. Then norm f is 0. So far so good. Now suppose norm f is 0. Can you conclude that f is the 0 function? No, you cannot. All you can conclude is that f is 0 almost everywhere. So now what you do is you say, you know what, I will work around this by thinking in terms of equivalence classes. So you know what an equivalence class is. Basically, you have a set. On that, you introduce an equivalence relation. Right? So an equivalence relation says that X is equivalent to Y if such and such is true. An equivalence relation has to have certain properties. Once you introduce an equivalence relation on a set, you can partition the set into disjoint equivalence classes. And then with each equivalence class, you can work with a member from that equivalence class, and that's exactly what we're going to do. So now we're going to say that in LP, declare functions f and g to be equivalent if f minus g is 0 almost everywhere. In other words, if f equals g almost everywhere. So we're saying that if two functions agree almost everywhere, we will blur the difference between them and think of them as the same object. So what do I want to say? So to have a chance of making this symbol a norm on LP. By the way, I wrote this last time, and I'm just going to remind you of this again. LP of omega f mu is LP of omega is LP of mu is LP. Okay, depending on if things are clear, then we may not want to write all this. We may just write LP. So if I write LP, then I'm thinking that I know and you know what the measure space is. Okay? And here in this case, you and I both know what the measure space is. Okay, so I'm just writing LP. Okay, so to have a chance of making norm P a norm on LP, we identify functions which are equal almost everywhere. All right, so what does that mean? I.e., say that f and g in LP are equivalent if f equals g mu almost everywhere. And now what you're saying is if this happens, then I will blur the distinction between f and g and I'll think of them as the same function. Okay, now there are certain things you would typically write down which I'm not going to write down. You will go back to what is a set. Okay, you know what a set is. Then you'll talk about what is a relation on a set. Okay, you can go back and look at an analysis book as to what a relation is on a set. Then you can talk about what is an equivalence relation. Okay. Well, once you have equivalence relation, you can talk about equivalence classes. So you can take any element of the set and you can ask which elements of the set are equivalent to it. That gives you an equivalence class. Then you can convince yourself that the set is the disjoint union of all equivalence classes. Bravo. I'm not going to write all that down. Okay. But that's what we're doing here. We're basically taking functions and throwing them into equivalence classes. So when I write f, what I really mean going forward is I'm talking of an equivalence class of functions, one of whose representatives is f. That means I'm talking of an equivalence class of functions where each function is equal to f almost everywhere. So for the purposes of integration, I can take f as a legitimate representative of that equivalence class. Okay. Now, in other words, LP of omega f mu is the set of all equivalence classes of measurable functions f mapping omega to r bar. I'm not saying which sigma algebra is involved, you already know that. Such that this symbol is finite. Now at this point you may say cheating, and I say yes, I agree. Here, if I'm talking about the set of equivalence classes of measurable functions, that is different from the collection of all measurable functions. So strictly speaking, I should change this L here. And maybe I should do something like here, maybe I should write LP or something. So this is just to remind you that In this case, we're talking about functions. In this case, we're talking about equivalence classes. But I am not going to make this fuss. Strictly speaking, okay. Strictly speaking, I should probably replace this LP by some other kind of L, because now I'm working with equivalence classes. So let me just write strictly speaking. But I am not going to make this fuss. Okay, I'm not writing any more comments on this. You have the video, so if you look at the notes and you're wondering what is the symbol doing here, you can go back and look at the video. Let's see how many minutes we are in. We're about, I don't know, 17 minutes or something in, and you can understand what this is. Okay, but I'm not going to do this. Okay, I'm just going to stick to LP. So some abusive notation is happening. Okay, so LP of omega f mu is the set of all equivalence classes of measurable functions f taking omega to r bar such that norm fp is less than infinity. So now when you're working with equivalence classes, what is the zero element? The zero element is the equivalence class of the zero function. What is the equivalence class of the zero function? The equivalence class of the zero function is the collection of all measurable functions which are zero almost everywhere. And so now, lo and behold, if norm fp is 0, we can safely say that f is the zero equivalence class. Okay? And so now we have some chance of getting a norm. Okay, so thus the zero element is now the class of functions. By the way, here I should say they have to be measurable, they should have domain omega, they should have range r bar. I'm not going to write all that, you know that background, which are zero almost everywhere. Maybe zero mu almost everywhere. All right, so now the trouble we ran into with this second part has been resolved, because now if norm fp is 0, we get that f is 0 mu almost everywhere. But wait, any function that is 0 mu almost everywhere is precisely the zero element of LP. Why? Because now we're thinking of LP not as a family of functions, but a family of equivalence classes of functions. All right, now one thing we'll do that you typically do is you will periodically go back and forth between equivalence classes and representatives of that equivalence class. We will find it convenient to take specific functions f, but when we get some results, we have to keep in mind that the thing may be true for all functions which are equivalent to f. Okay. So what is the next order of business? The next order of business is to work our way towards something called Holder's inequality. Okay, you have probably seen this. Fairly certain you have seen this. This is very important. Now, once you get Holder's inequality, you get something called the Minkowski inequality. Now, what is the use of the Minkowski inequality? Well, Minkowski inequality basically gives you this triangle inequality for these LP norms. Okay, so we've taken care of one. Once we do Holder's inequality, we'll get Minkowski's inequality. Once we get Minkowski's inequality, we will have 3. So what is left is only 2. And we will see that 2 is not hard to do at all. Okay? So that will basically convince us, that will complete our argument that these things that we think of as norms are in fact norms. Okay. All right, so now to do Holder's inequality, we will need this lemma, and this is called Young's inequality. Okay, a quick question. Have you seen the proof of Young's inequality in the functional analysis course? Anybody? Anybody listening? Anybody who goes to the functional analysis course?
No, sir.
No, you have not seen the proof there? How many of you are in functional analysis?
I have also taken.
What's that?
I have also taken functional analysis.
But did you see the proof of Young's inequality?
Not in functional analysis, but in major theory, I have seen the proof.
You saw the proof. Was that here or somewhere else?
Yeah, here only.
And how about you, Saraswati? Have you seen the proof of Young's inequality?
No, sir.
No. Okay, so then let's go through the proof of Young's inequality. This is not a measure theoretic proof. This is kind of classical calculus proof. But anyway, so since at least two of you have not seen it, it may not be bad to do this. Okay, so Young's inequality says the following. So here's your lemma. For P and Q in the open interval 1 infinity, just a second. Okay, that's fine. 1 infinity with 1 over P plus 1 over Q equals 1. And for any x, y in the interval 0, infinity, we have the following. X, y less than or equal to x to the p over p plus y to the q over q. Okay, so let me throw in this term here that will make the amount of talking I have to do and the amount of writing I have to do less. So suppose P, Q belong to the closed interval 1 infinity with 1 over P plus 1 over Q equals 1. Then P, Q are said to be conjugate exponents. Now, at this point, you may say this sounds kind of silly. I don't see anything being taken to any exponent, but again, we're talking about LP spaces. So remember, we'll be taking functions and taking their pth power or taking their qth power or so on. So I expect you to now know this. Suppose P and Q are real numbers in the closed interval 1 infinity. Note that it's closed at both ends. With 1 over P plus 1 over Q equals 1. Of course, 1 over infinity is 0. Okay. Then P and Q are said to be conjugate exponents. So basically this is saying suppose P and Q are conjugate exponents, and here actually you're insisting that they are in the open interval 1 infinity. Then what you have is for any x, y non-negative, x, y is less than or equal to x to the P over P plus y to the Q over Q. One look at this and you realize that it can't be true when P or Q is infinity because, well, then you're in trouble. All right, so let's go through a proof of Young's inequality. Again, I may end up just glossing over a few points. So proof, a result is clearly true if either x is 0 or y is 0 or both. I'll leave it to you to check this. By the way, note that this Young's inequality that we're writing down, this does not have any measure theory flavor. Okay, this seems like a classical analysis thing. All right, so now we'll have to consider the case when x is not 0 and y is not 0. So suppose x is not 0, y is not 0. All right, so now here's what I'll do. I'll fix y in 0 infinity. Well, I've already said that y is non-zero, so I'll just take the open interval 0 infinity and let f of x equal x to the p divided by p plus y to the q divided by q minus xy. All right, remember here y is a parameter, okay? Y is fixed. So this is really a function just of x. Now, of course, this function is meaningful even when x is 0. However, we are only working with x non-zero at this point, right? So note that f is C2 on the open interval 0 infinity. Okay, now remember here f is just a function of x, okay? Y is fixed as a parameter. And what else is true? With f prime x equals x to the p minus 1 minus y, and f double prime x equals p minus 1 x to the p minus 2, which by the way is positive for on 0 infinity. Okay. Let me avoid any possible misunderstandings. If I say positive on 0 infinity, somebody may think that I'm saying this is positive and this is positive on 0 infinity. That is not what I'm saying. I'm only saying that this guy is positive on 0 infinity. Okay, so let me say that clearly. Note that f is C2 on 0 infinity with f prime equals this, f double prime equals that. Again, this just comes from straightforward calculus. You're treating y as a parameter. Okay. Note that. Of course, this is not good to use the same phrase all the time, but that's all right. Note that f double prime of x is greater than 0 on the open interval 0 infinity. All right, so what does this mean? This means that thus f is strictly convex. Okay, what is a convex function? Suppose I have f which takes the real line to the real line, right? I have a convex function, so I draw its graph, right? The function is convex if the graph always lies below the secant. Okay. All right, so thus f is strictly convex, and by the way, a sufficient condition for strictly convex is that the second derivative be strictly positive. Thus f is strictly convex and has a unique minimum at x0, where x0 in 0 infinity satisfies it satisfies what? It satisfies f prime x0 equals 0. Okay, this is not news to you. Okay, you studied this when you first learned calculus. If I have a real valued function of a real variable and I want to find maxima and minima, I take the first derivative, set them equal to 0, solve, examine the second derivative there, and then accordingly decide whether it's a maximum, minimum, or neither. Okay, so the unique minimum must happen where f prime x0 is 0. By the way, if f prime x0 is 0, that means what must happen? I.e. x0 to the p minus 1 minus y is 0. I.e. What do I have? I have x0 equals y to the 1 over p minus 1. Any questions with this? Okay, so where does this unique minimum occur? It occurs at this particular point. All right, so the question is, what is this minimum value? Let's find out. This minimum value what is this minimum value? This minimum value is f of x0 equals x0 to the p over p plus y to the q over q. Right? Remember, so far we have fixed y, all right? And we're just thinking of things as a function of x, minus x0 y. But wait, we know what x0 is in terms of y. So we'll say now x0 to the p is going to be y to the p over p minus 1. I think you believe that. If x0 is y to the 1 over p minus 1, then I take pth powers on both sides here. I'll get x0 to the p is y to the p over p minus 1. But 1 over q is 1 minus 1 over p, which of course is p minus 1 over p. And so what you get? So you get q equals p over p minus 1. So what does that mean? Thus, x0 to the p equals y to the q. So far, so good. Any questions? All right, now we're going to come back into this thing, all right? So this is where we're coming back. We fixed y, so first we said that if x is 0 or y is 0 or both are 0, then this is trivially true, so problem solved. Now suppose the case when x is not 0 and y is not 0. Okay, now fix some y in the open interval 0 infinity and look at this function of only one variable x. Now play with this using the tools of classical calculus, first derivative, second derivative, etc., etc. Convince yourself that this function has a unique minimum at some point x0. Now that x0 better be related to this y, and it indeed is, and what we have shown is that x0 to the p must be y to the q. Okay, so now let's come back to this. By the way, any questions so far? Okay, so now let's come back to f of x0. So I think I'm going to need a bit of space to write, so let me move this so on to the next page. So f of x0 ends up being y to the q times 1 over p plus 1 over q minus y to the 1 over p minus 1 times y, and this ends up being y to the q minus y to the 1 plus 1 over p minus 1. By the way, here then, I'll leave it to you to sit down with pen and paper and convince yourself that this is what happens. This is basic algebra. I'm sure all of you can do it. And so what you get is you get y to the q minus y to the, here I'll get p minus 1 plus 1 over p minus 1. So this is y to the q minus y to the p over p minus 1. But wait a second, p over p minus 1 is just q. This is just q. And so you get 0. All right, any questions so far? Okay, now this, remember, is the smallest that the function f can get. Fix any y, this is the absolute smallest the function can get. So if you fix y and let x be anything, the smallest you'll get is 0. Which means if you let x be anything and y be anything, the smallest the function will get is 0. So hence, f of x equals x to the p over p plus y to the q over q minus xy is greater than or equal to 0 for all x, no matter what y is fixed. And so in other words, for all x, y in 0 infinity. And so this exactly proves what you wanted to prove, right? Remember, Young's inequality said that this quantity xy was less than or equal to this guy. And of course, that's what you get if you take this equation and you just rearrange it. Any questions so far? Questions? All right, looks like no, so let's go on. So this is going to be our one of our tools in proving Holder's inequality. So let's basically prove Holder's inequality. So basically, I kind of like Holder's inequality. Right? So let me do the following. Before I'll state Holder's inequality multiple times. So what does Holder's inequality say? Okay, so you have conjugate exponents. P and Q. Okay, so that basically means that P and Q belong to the closed interval 1 infinity, 1 infinity with 1 over P plus 1 over Q equals 1. Okay, now what Holder's inequality says is that if F is an LP and G is an LQ, then FG is an L1 and gives an estimate for the L1 norm of FG. By the way, I should be maybe a little cautious before saying L1 norm because we haven't yet proved it's a norm, but as I said, it's going to be a norm. So this is what Holder's inequality does. It says, suppose you have P, Q in the closed interval 1 infinity with 1 over P plus 1 over Q equals 1. In other words, suppose P and Q are conjugate exponents. Now, of course, you're working on a fixed measure space. Okay? Suppose F is an LP and G is an LQ. You can be sure that FG is an L1. Holder's inequality tells you that. Further, it gives you an upper bound for norm FG1. So let's write it down, write it out nicely now. So theorem, this is Holder's inequality. All right, so let P Q be in the closed interval 1 infinity with 1 over P plus 1 over Q equals 1, and let F be in LP of omega F mu, G be in LQ of omega F mu. Okay, note that the measure space is the same here, okay? You can't do something like take F on one measure space and take G on another measure space. Can't do that. All right. Then F times G is in L1. Again, let me, since I'm making a fuss about which measure space, on the measure space omega F mu, and the norm FG1, and again, remember at this point, this is just a symbol. We don't yet know it's a norm, is less than or equal to the norm symbol F sub P times the norm symbol G sub Q. All right, very nice, very neat. Let's prove this. All right, so maybe this theorem should get a little decoration, perhaps. Let's underline it. Ah, that's good, much better. All right, so now let's prove this. All right, so first we'll consider the case where P is 1, Q is infinity. Okay, now of course, if I do the case P is 1, Q is infinity, the argument will be the same when Q is 1, P is infinity, except the roles will be reversed. So I just need to do one of them. So first consider the case when P equals 1, Q equals infinity. All right, so what does this mean? This means that G is in L infinity. So since G is in L infinity, by the way, so now we have made it abundantly clear that we are always working on this fixed measure space omega F mu. Throughout Holder's inequality, the measure space is fixed, so I'm not going to say which measure space is involved here. L infinity, no, it's the same one. Okay, so since G is in L infinity omega F mu, there exists K greater than 0 such that absolute value of G less than or equal to K mu almost everywhere. Okay, remember L infinity means that the function is bounded almost everywhere. That is a little funny way of saying it. But what that means is you can find a number K such that the absolute value of the function is less than K almost everywhere. Okay, so this is true. So now what happens? So thus, absolute value of F times G is less than or equal to K times absolute value of F almost everywhere. Okay, now since integral absolute value of F is finite, integral absolute value of Fg, which is less than or equal to K integral absolute value of F, is also finite. Thus, Fg is in fact in L1. By the way, measurability was never an issue because you have already learned that if I take a product of two measurable functions, I'll get a measurable function. So given that F and G are measurable from the get-go, F times G is measurable. Okay. Further, what's going to be true further? The norm Fg1 is going to be less than or equal to K times norm F1. Why is that true? Well, actually, that's already present here. Right? Because if I look at this highlighted equation in blue, this quantity is just norm Fg1. And this quantity is just norm F1. All right, so we're almost done. So we get norm Fg1 less than or equal to K norm F1. Now take inf over all such k. Now what do I mean by such k? I mean k satisfying this thing. All right, so when I say such k, all such k, I mean all k which satisfy this thing. And there is at least one k which satisfies this thing because G is in L infinity. Now take inf over all such k to get norm fg1 less, something like that, 1 less than or equal to norm f infimum of all k such that absolute value of G less than or equal to k mu almost everywhere. But wait a second, this guy is simply norm G infinity. All right, so i.e. norm f G 1 is less than or equal to norm f 1 norm G infinity, and we're done. Of course, the argument when P is infinity, Q is 1 is similar. I will obviously not go over that. All right, so now we want to consider the case where P and Q are both in the open interval 1 infinity. Questions so far? All right, so now consider the case when P and Q are both in the open interval 1 infinity. So when P is in the open interval 1 infinity, Q is in the open interval 1 infinity. All right, so now I want to prove Holder's inequality, right? So the first thing I'll do is let me get rid of the trivial case. So I claim that if either norm f is 0 or norm g is 0, then this is trivial. Well, why is it trivial? Suppose norm f is 0. That means f must be 0 almost everywhere, which means fg must be 0 almost everywhere, which means left side is 0, right side is 0, and so the inequality holds. Suppose instead norm g is 0. That means g must be 0 almost everywhere, which means fg must be 0 almost everywhere, which means norm fg is 0, 0 less than or equal to 0, it is true. So this is trivially true in the case when norm f is 0 or norm p is 0, okay, this is trivial when norm f is 0 or norm g is 0 or both are 0. So we will look at the case where both are non-zero. So if either norm f p is 0 or norm g q is 0 or both, of course, claim is trivial. All right, so basically we can just assume that norm fp is strictly positive, norm gq is strictly positive. So assume that norm f p is strictly positive, norm g q is strictly positive. So far, so good. All right, so now what are we going to do? So now, oh wait, what did I do? All right. Okay, so what I basically need to do is I need to take some of this and put it on the next page. Right. Okay. And I'm going to need to do a little more rearranging. Okay. Now we're good. All right, so now consider the case where P is in the open interval 1 infinity. When P is in the open interval 1 infinity, Q is in the open interval 1 infinity. If either norm F is 0 or norm G is 0 or both are 0, the claim is trivial. So assume that both norm F is positive, norm G is positive, strictly positive. I mean. Then what I'll do is I'll define these new functions. Define capital F of x to be absolute value of small f of x divided by norm fp, and define capital value of g of x to be absolute value of small g of x divided by norm g q. By the way, we've just convinced ourselves that the denominators are non-zero, all right? Because we showed that if either the denominators is 0, Holder's inequality is true, our job is done. Okay, so now what we'll do is we'll use Young's inequality. Now, by Young's inequality, excuse me for doing that periodically. You know that because of the sensors and all, if I don't move too much, the lights just go off. So I have to periodically, wave my hands and legs so that the lights come back on. All right, so now by Young's inequality, what you'll get is f of x times g of x is less than or equal to f of x to the p divided by p plus g of x to the q divided by q. Okay, keep in mind here that capital F and capital G are non-negative. Okay, there's no chance of them going negative because they involve an absolute value. All right, so now what am I going to do? I'm going to just write this out in terms of the small f and small g. So what does this imply? This implies that absolute value of small f of x times absolute value of small g of x divided by norm f p norm g q is going to be less than or equal to 1 over p, okay, absolute value of f of x to the p divided by norm f p to the p plus 1 over q, absolute value of g of x to the q divided by norm gq to the q. Any questions so far? All right, so remember that this quantity is simply this quantity is simply this, and this quantity is simply this. All right, so now I'll just integrate both sides. So this implies that the integral absolute value of f of x, absolute value of g of x divided by norm fp, norm gq is going to be less than or equal to 1 over p, 1 over norm f p to the p, integral absolute value of f of x to the p, plus 1 over q, 1 over norm gq to the q, integral absolute value of g of x to the q. Any questions so far? And now you stare at this for a second and you realize what this is. This is simply norm f to the pth power. You stare at this and you realize that this is simply the norm g in LQ to the qth power. Okay, and so as you can see, we're going to be done, right? Because now what's going to follow is, let me just use a different color. This and this are going to cancel because they're the same. This and this are going to cancel because they're the same. And so what you see is that the right side of this equation is simply 1 over p plus 1 over q, which remember is 1. Right? All right, and so we're done. Right? So what this means is we get that the integral absolute value of f of x, g of x. Remember that absolute value of f times absolute value of g is same as absolute value of f times g. This is going to be less than or equal to norm FP, norm GQ as claimed. Right, now, so what does this mean? Let's just stare at this. First thing this is saying is that if I take absolute value of Fg, okay, now remember that this quantity is finite. So what does this mean? This means that integral absolute value of Fg is finite, which means absolute value of Fg is an L1 function. Hence, Fg is an L1. And then you look at this and you ask yourself, what is this? Well, this is nothing but just the norm of Fg1. And norm Fg1 is less than or equal to norm Fp, norm GQ. And that is precisely Holder's inequality, which is what we wanted to show. Any questions? All right, so next time we'll do Minkowski's inequality, and we'll see how putting all the pieces together, you quickly get that this symbol, which we have been cautiously calling a norm, is in fact a norm. All right, so I'll stop sharing the screen right here and the recording, and I will see you on Wednesday.